Okay, let's take a very practical example again and try to think about voltage dividers for strain gauges. As we saw before, the way we use a bonded strain gauge to measure strain in a body is to stick it to the surface of a body. So assume that we want to measure the force F here. One way to do it would be to use a cantilever structure. We take one end of the beam and fix it to a solid structure, and then we apply force to the other end of the beam. And what happens when we apply force? This beam will bend. And we can measure this bending by seeing how much the surface, the upper surface, expands. And to do that, we bond the strain gauge on top of the beam. Okay, let's assume that the gauge factor of the strain gauge is 2. Now remember that the gauge factor is the change in resistance, the relative change in resistance divided by the strain. So what is the relative change in resistance? It's 2 times the strain. And if the maximum strain that a strain gauge can take is approximately 3%, what is the maximum change in resistance that you can expect? Of course, you can see that if you put that through this equation, you get the maximum delta R by R to be around 6%. So let's take the strain gauge now and put it in a voltage divider and see what happens. So here's a voltage divider. We have taken that strain gauge that we looked up in the previous slide, and we have put it at this point. And instead of writing R plus delta R, I have written it as R1 plus X, where X is the fractional change of resistance. Okay. So what is the output of this voltage divider? You can very easily see that V output is going to be R0 1 plus X divided by RF plus R0 1 plus X into V. Okay, and if we make the assumption, if we say if RF over R0 is equal to K, we can rewrite this equation in this form. Okay, having done this, maybe what we can also do is we can make some assumptions. And if we assume that X, our fractional change in resistance, is much less than K, we can write this V output in this form. We can write it as 1 plus X, and essentially we can ignore this X because it's much smaller than K, and we can write 1 plus K V. Okay, and this means that our output voltage is going to be V over 1 plus K plus X over 1 plus K V. The same maths that I've done is just typed out here to be more clear. And now you can see that the output voltage consists of 2 parts. One is a fixed part and another is a variable part. Now what we are interested is the change in resistance, and the change in resistance is basically given by this variable part of the voltage and not by the fixed part. Which means that when it comes to amplifying this output, so here's an amplifier, our non-inverting amplifier connected to the voltage divider, and what we want to do is we only want to amplify the variable part, because it's only the variable part that has information about the change in resistance. We do not want to amplify the fixed part. But the variable part is 6% of the fixed part, because the value of X is 6% or 0.06. So which means that we have to amplify this small signal in the presence of this large fixed signal. How are we going to do that? So just to make things a little bit more clearer, just think about this voltage divider here. Okay, let's assume that the fixed resistance is 500 ohms and the base resistance of the strain gauge is 500 ohms, and we have a change of just 25 ohms. Okay, if we assume that the voltage that we are giving is 5 volts, then the output voltage, the fixed output voltage is 2.5 volts and the variable voltage is 0.06 volts. So now what we need to do is we want to amplify the 0.06 volts in the presence of this 2.5 volt signal, which we don't want. And this is not a very easy thing to do. But that doesn't mean that it's not doable. It's actually fairly straightforward if you think about it for a moment. What we need to do is we need to subtract the 2.5 volts out of this total signal and then amplify whatever remains. So we found out a way of amplifying the very small change of resistance that a strain gauge gives in response to a deflection. Now let's think of other problems with voltage dividers. One other problem would be the problem of source impedance. What happens if our source, the 5 volt source here, has a 10 ohm source impedance? Then instead of having 2.5 volts at the output, you have 2.475 volts. So depending on the source that you use, your source impedance can change. And if the source impedance changes, the output of your voltage divider changes, and you don't know whether the change is because of the changed resistance or because of the source impedance. So there are two problems that we looked at with voltage dividers. One was the problem of source impedance, and another was the problem of amplifying the very small signal in the presence of a large fixed signal. Now both these problems are dealt with in the next method that we are going to use. But for that, the next video.